collaboration between our team from NUS and Toka Labs, which is a trading firm on the blockchain space in Singapore. We focus on the detection of arbitrage opportunities, which we model as negative cycles in token graphs. So today's presentation will cover the introduction of this project, background and related work. Then I will introduce some of our main algorithm designs with 2 optimizations, followed by experiments and our conclusion and future works. So arbitrage is the exploitation of the price difference across the markets to secure the profit without risk. So it plays a critical role in the financial systems, and previously we can see it in the foreign exchange market and also in the stock market. While in recent years, arbitrage in the crypto market has been emerged. And I showed 2 examples here to help understand better what is arbitrage and what is the clinical arbitrage is defined in our work. As we can see from the left side, it shows an example in the foreign exchange that includes 3 currencies: the Japanese yuan, the Russian ruble, and the British pound. And we can see that with the input 100 Japanese yuan, because of the exchange rate of these 3 pairs of exchange, finally it just came out with more output than the input, so makes a profit. And very similarly, this can happen in the crypto market, as I show in the right figure, is including the Bitcoin, Ethereum, and Litecoin. But there are 2 points I want to highlight about the crypto market. One is that the trader, they actually don't want the arbitrage cycle to be too long. This is for control the risk of some failure of the execution, and also about don't want the gas fee to be too high. And the second thing I want to highlight is that what makes crypto a little bit different is that in the decentralized market, all the price is controlled by the AMM curve, so it is not controlled by any centralized governance. So this will make the market change very rapidly, and with any swapping or removing or adding the liquidity by the liquidity provider will change the exchange rate. And in this work, we focus on the arbitrage detection in the cryptocurrency market with real-time and openly available data. So with our collaboration with Toka Labs, we come up this data pipeline for the arbitrage in crypto market, which can be used as a generalized pipeline for the industry. It includes 4 steps, starting from we have gained some data about the liquidity pools on the decentralized exchange. First step is to build them as a graph, which we can see that the nodes represent the tokens and the edges represent that there are some tradable pairs between these 2 tokens. Then we will do the cycle detection. Actually, we'll do the K-hop negative cycle detection, which can transfer to an arbitrage opportunity later. I will share more details how it transfers. And then we will execute a trade along the profitable cycles, and this process will be done iteratively block by block. Among these 4 steps, we find that the second step, which is the detection of the K-hop most negative cycle, which we call KMNC, is the key to secure real-time and scalable arbitrage. But there are 2 major challenges that current literatures face. The first one is that this challenge is actually a very high computational complexity. It is actually an NP complete problem. This means that in the worst case, no polynomial time algorithm can guarantee that the exact solution unless P equal to NP. And this difficulty grows rapidly as K increases, as we can see from the left figure in figure 2. It shows the weight distribution of all the K-hop negative cycle in the crypto graph, while the weight are actually quite skewly distributed. So if we just trying to enumerate all the cycles and find the most negative one, it won't be, it will be very ineffective and efficient. While the second challenge is related to some existing methods, is that many state-of-the-art approach, they try to find some localized search or use some greedy heuristic to do the detection. However, these methods explore the subgraph around the beginning point, but often fail to escape the local optimum within a short time. So as we can see from the right side figure, what they do is that they're very likely to stuck in the local trap for a long time. And that's why we need another method to handle both effectiveness and efficiency of the detection. Before we go into the algorithm, I will cover some background about our method. So first about the token graph, it is a directed and weighted graph. The vertices are tokens and edges are the traceable pairs. And within this graph, we can find what we call clinical arbitrage. It refers to the process of exploiting the price discrepancy in the cycle of token exchange to generate the profit. And it will lead to a simple cycle in the graph. A simple cycle means that there are no repetition of any node on the cycle. So in the sequence of vertices that represent the graph, the cycle, only the first starting node can repeatedly happen in the end. Other nodes will not repeatedly see. With the graph, we will define the edge weight to represent the exchange rate between these two tokens. To facilitate the efficiency of the cycle detection, we actually will use this minus log transformation of the exchange rate to represent the weight. The reason why we do this is that actually in the product space, arbitrage will correspond to cycles where the product of the exchange rate is greater than 1. Which means we can got more output than the input. And after we do the log transformation, that will become simply a cycle whose weight sum less than 0. And a more negative weight usually corresponds to a more profitable opportunity. I'll use another. I think maybe some formatting. I'll use this example to show how this transformation works. So it's the same example I've shown in the introduction. With the exchange rate, the input of the Bitcoin will increase in the output. And if we do the log transformation, it will just lead to the sum of these weights smaller than 0, which we call them negative cycles. So with this transformation, it allows us to formalize this financial data science task as a graph-related problem, which we call K-hop most negative cycle detection. The input is a directed weighted graph and hop constraint K. The output is to find a simple cycle of exact length key with the most negative total weight. So this is an NP complete problem. There are some related work with regards to the negative cycle detection and crypto arbitrage detection. Basically, there are 3 types of work. The first one is that there are some classic graph algorithms that are trying to detect the negative cycle in the graph. However, most of them working on trying to find whether there is a negative cycle or there is not, but they do not regard to what is the most negative one. The second type is that there are some work they do cycle enumeration, or some of work they do path enumeration when they fix the source and the target token. But these works, they are doing their enumeration, there will be a large use of memory and also time. The third type of the related work is crypto arbitrage detection. So there are actually a few methods. They are designed specifically for the arbitrage detection in the crypto market. But most of them, they are trying to rely on some heuristic or local search. Again, it will be limit the scalability and accuracy of their method. Therefore, they actually lack some approach that can balance the efficiency and effectiveness well. And this is why we design our reach. So I will cover a high-level framework of what reach did. Basically, it combines several techniques. First, we will use the randomized color coding method to sample the simple K-hop cycles. The color coding method will help to avoid the redundant paths and focuses the search on some validated candidate cycles. Then we will apply a dynamic programming approach to avoid recomputing the partial paths. After that, we designed two specified optimizations. They are tailored for color coding methods, and all of this work together to make Rich both theoretically and sound and empirically efficient. Let's look deeper to each of them. The first one is the color coding. The core idea of color coding is actually very simple but very powerful. So as I show in the figure 5, it shows 4 instances of the color coding. In each coloring instance, all the nodes will be randomly assigned one of the K colors. There are total 3 colors, and in each instance, the algorithm will only look for cycles where all the nodes have different colors. So in this way, it will decrease the search space a lot. And by randomly assign colors to different instances and repeat the instance, we can ensure that the most negative cycle can be found. A very important lemma here is that any K-hop multi-color cycle in the graph is necessarily a K-hop simple cycle, which can potential to be our final optimal of the KMNC. So let's say prime to be the KMNC in the graph G. If all its vertices got distinct colors, as we call them the multicolor cycle, then in every instance it says to be the most negative one. This will happen with the probability K factorized divided by the K to the power of K, because like each node will have K options to be colored, and in total there will be K to the power of K combinations. And actually across the multiple coloring instance, which we give it L instance, if the global KMNC is colorful in any one of the instance, then the final algorithm will detect it, so we will never miss it. This will lead to a detection probability that related to 2 factors in the end. One is the L, which shows the color coding instance, and the other one is K, which shows the length of the cycles. For example, when we set L to be 30 and K equal to be 4, the detection probability will more than 95%. With the probability guaranteeing, we will still need a way to actually find the most negative cycle within each instance. And the basic solution here is that we can use DFS to do that. So how this DFS do is that basically it is initialized from every vertex in the graph. And for each step, we'll examine the neighbors of current vertex. If the neighbor's color already exists in the past and it is not the star, then we will just skip it because it cannot fulfill our multicolored cycles. And then otherwise, we will append to the neighbors and update the cumulative weight and check if the paths form a K-hop cycle. If so, it can form a K-hop cycle. We'll compare with the best that we got now and to see which one is the final answer. However, using DFS here will lead to some redundancy. Very obviously is that when we start from each node, some of the subpaths, they will be revisited multiple times as they are shared by different such branches. So that's why we come out with our second very important strategies is that we are trying to use dynamic programming here to do the cycle detection. So in our dynamic programming table, what we design is that the state of the DP will be store the minimum weight of any valid path ending at vertex V with the color sequence alpha p, while V is the current vertex in the path and alpha p includes the colors of the nodes in the current path. And the transition of the DP table will only keep the minimum weight for each state. The time complexity of this will just be O2 to the power of K, then times V times E. I will use an example to show, because I know if I just say it's not that easy to understand. So see this figure 6. In this example, I'm trying to find a graph, a cycle with K equal to 4. So we can see there are total 4 colors in the directed graph, each with its relative edge weight. So what this DP table do is that it just finds the most negative weight round by round, starting from V0. The first round it will go to V1 and V2, and their weight will be -1. The second round it will set to V3, but here we'll see that there are actually two paths then from V0 and reach the V3, but they actually share the same colors. So the DP will only store the one with minimum weight, which is -3. And then it will reach V4, and finally the algorithm will find that it can form a cycle now because already 4 colors in the DP table. So it will find that finally there are 2 cycles, but again, DP will just store the most negative one, which is C2, formed by V0, V1, V3, V5, and V0. So in this way, we can see that this part of the computation will be saved because the DP can store the intermediate best path from V0 to V3. Okay, so this is how the reach is mainly doing in its core algorithm, but we still develop 2 important optimization that further enhance the efficiency of reach. The first one is the bitwise encoding. So in reach, what we do is that we will represent each color set as a bit mask rather than using any set to do that, because we found that this will be more efficient, especially when we are trying to do some color checking and color addition in the DP table. There are actually millions of times of color checking and addition in the DP transition, as I showed before. And as we can see from the figure here, after we did this bitwise encoding, the checking and addition will just transfer to AND operation and OR operation in the bitwise encoding, and it can be achieved in the O1 time. The second optimization we do is to do a graph reduction. So the key insight here is that certain nodes, they can never appear in the final multi-color cycle. So we just remove it before we really do the search. For example, if a node has only one valid label and both of them share the same color as V3 and V6 in the example, then these 2 nodes can actually never be in the final KMNC because it can never form any multicolor cycles. So we will just remove them. And moreover, this process can actually be done iteratively until the end. What we did, the real search will only include the nodes and the edges with the real potential that can form the KMNC in the end. So this will help us to decrease the size of our searching graph a lot. Okay, with all this in mind, let's look at some of our experiment results. First, about the experiment setup. So to evaluate reach, we actually conducted extensive experiments using the token graphs that we built on the Uniswap V2 pools. So Uniswap is one of the most popular and famous decentralized exchange on Ethereum. And we select 6 datasets. Each of them represent a market state of different block. The largest one is Uni6, which include about 360K number of vertices and 730K number of edges. And we compared with 4 major baselines. They are the start of art from the related work we shared. They include some path enumeration and some algorithm that design specified for the arbitrage in crypto. The metrics we measured is in 2 perspectives. One is the detection time, which shows the efficiency of our methods, and the other one is the most negative cycle weight, which shows the effectiveness of our methods. We will measure the relative error of the weight that reach find compared to the optimal one. And the first setting is to set k equal to 5 and with 30 color coding instance. But we also do more experiments using longer k and larger instance. I will show the results later. So our first result focused on the efficiency of reach. What we did is that we compared the detection time of reach and the baselines across all the 6 data sets, and we can find that reach can consistently outperform all of the competitors. On the smaller graph, the speed up is more or less like 1.6 times, while on the largest, it can beat the second best around 32 times up. To give a closer look at the impact of the cycle K, we look at how the performance in the efficiency change with the K increased to be from 3 to 6. We can see that reach runtime grows much slower than the baselines, but some difference can be seen that when we compare reach with those enumeration-based methods, it demonstrates increasing advantage as the K grows. While when we compare it with some grading methods, it can maintain an average, but the grading methods, they are quite moderate. However, what we find is that those grading methods, they cannot guarantee to find the best result, the optimal results. And what they do is that they will decrease the searching space when the K is larger. Second experiment about the scalability, which we can see that reach scales linearly with the graph size, while the baselines quickly become infeasible or will become time limit exit. Compared to the second best method, as I have shared, that reach can achieve a substantial speed up, ranging from 1.6 times to the 32 times on the largest. After that, we did an ablation study to see that each part of our components, whether they are working or not. The first thing we do is that we compare the algorithm with dynamic programming and with DFS. We can see that Reach can achieve about 1 to 4 times speed up over DFS. This is because it saves a lot of searching and redundant subpath searching using the dynamic programming table. And then we compare our full reach with removing each our optimization. First, removing the bitwise operation, we can see that the runtime actually slows a lot. It slows about 50% to 90%. So we can see that impact of the bit operation is quite impressive, and impact actually grows with the graph size. When the size is bigger, we will do more bit operations, so its efficiency will also show more significantly. And the second ablation study we do is that we remove the graph, we're doing the graph reduction, and the runtime here slows by 2% to 9%, around 10%. But actually, we see that the graph size will be decreased about 20%, even though the efficiency only got less than 10% as advantage. This is also reasonable because when we are doing those graph reduction, the node that being reduced is anyhow not very high connectivity. So removing them from the graph will not give a direct impact to the runtime. If we remove both of our optimization, the runtime will slow by 60% to 99%. So this confirms that the optimization are complementary and they are jointly critical for our final complete version of it. And after we did the experiments on runtime, we also measured the memory usage. So theoretically, the memory of running Reach will grow with both the graph size and the cycle length. But we found that Reach remains efficient in practice, even on the largest graph with K equal to 6, it still represents less than 1%. It's around 2 GB some on our experimental server. That's all about efficiency, but efficiency is only valuable if the accuracy can be preserved by our algorithm. So we further explore the effectiveness of Reach. As I show in the table 4, it compares that the most negative cycle detected by each algorithm. As the Brady one actually can detect the optimum, we compare the most negative cycle detected by Reach with Brady to see how large is the relative error. we can see that among all these 6 data sets, the relative error is smaller than 4%. In some cases, it's smaller than 1% and even 0. This shows a very impressive result as REACH is actually not a very, it's not designed to be an accurate method, but a probabilistic method. And another important parameter that can influence the effectiveness is the number of instance L. As we have shown before, the probability guarantee is designed by K and L. Theoretically, the number of L required to detect the KMNZ phi prime depends on how long is the cycle and depends on the design detection probability. So through our experiments, we increase the number of coloring process L to see whether the relative error can drop. As shown in the figure 12, we can see that the error can actually drop very quickly at the beginning, and with L equal to 30, it can already achieve a relatively near optimal result. That's also why we set L to be 30 as our default setting. Finally, we also examine the trade-off between the runtime and the solution quality. So basically for REACH, the coloring instances are assigned randomly and detection time will just be proportional to the number of coloring instance L, while for other algorithms, when they cannot complete in the time constraint we set, we'll just detect the most negative cycle that can be found in that time constraint. We set the time constraint to be 50 seconds here because 50 seconds is more likely the longest time that a block on Ethereum can take. But actually, most of the time is even smaller than 50 seconds. So we can see from the figure 13 here, while other methods are still stuck in the local optimal, REACH can already achieve near optimal within a very short time. So this again highlights that REACH can rapidly detect the near optimal cycles to be practical in real case arbitrage. To conclude, REACH addressed the problem of detecting the K-hop most negative cycles in large cryptographs, and our experiments on the Uniswap dataset showed that it can achieve an up to 30 times faster than the state-of-the-art and baseline, and with near optimal accuracy. So beyond cryptocurrency, the technical in REACH can actually have broader applications like in other financial domains or in the transportation networks as well. And they may also be used for in some general graph analysis tasks requiring the constraint cycle detection. Overall, it demonstrates how the theoretical algorithms can deliver a practical impact in the crypto market. But the disclaimer is that it's only for academic use. Any practical deployment must consider the markets and regulatory risks. Finally, I'd like to share some of our future work and future direction. Firstly, is about the dynamic graph. So currently what we did is still in a static graph that is built on the crypto markets, but as we all know, the market is highly dynamic, and within every block, there will be new transactions, new swapping or adding or removing the liquidity in the pools. So the edge weight of those pairs actually change quite often, but the structure of the graph is rather stable. So what we try to tackle at this properties is that we are trying to design some incremental updates for the color coding and also for the dynamic programming stage. And the second direction for our future work is that we're thinking about making the algorithm parallelization. This is because that all the coloring process and all the DP in each instance will be independent from each other. So it will very naturally to do that in parallel. And another direction in the parallelization is that since the graph now is rather big, we can do some graph partition and using some exact methods or using REACH in each part of the graph. But this will bring some trade-off naturally, because when we're trying to improve the scalability, when we break the cycles to when we partition the graph to different parts, the cycles may be break. Okay, that comes to the end of my presentation. Thank you for listening, and I'm welcome to any questions or discussions. Any questions I can take?
I think it's like really interesting research. I have like a few questions. The first one is like, do you guys think about like your deployment and what kind of like the downstream force?
Yes, actually we have, this is a joint work between our team and the trading firm. So all the deployment are actually done by the company. And of course, there will be quite a lot deployment constraints. Like even though we can do the detection very fast, the speed of the transaction, how they want to want the transaction to be placed in the block are also very important. And the time of that part is also very critical. And any chances of the execution failure will just lead to the failure of the final arbitrage cycles. And that's quite a lot market conditions that real deployment must consider.
Let's see, like we can have like, well, we can increase like the computation, but like it is like the algorithm fast enough to detect it and place in that block.
Actually, we have discussed with the company, and they will say that how long time they can take for the detection of the cycle, and how long time they will need to really do the execution of the trades. That's how we are trying to do that in real.
Yeah. Second question. So in my understanding, so this question is kind of like we have like a graph and we're trying to find like a loop or like stop graph, which kind of like you closed and like the value of like the edges added is like the most active. Right?
Yes, correct.
Yeah. So and I think like this research proposed kind of like exploration algorithm. Is that what?
It's
Is
what
the idea?
I think the problem statement is quite accurate, is that we're trying to find the most negative cycle in the graph. But the searching space, if we search all of the graph using like DFS or some traversal method, that would be very high. So we're trying to use these color coding methods to decrease the searching space for each instance. And then we're trying to repeat multiple instances to increase the probability of finding the KMNC in the end.
I don't know if it's like a possibility, but I mean, let's say like we have like the most negative graph kind of like marked one, right? And like we have like the software quality, right? So like it's kind of like doing like the classification of software within like a huge.
You mean doing some subgraph mining to do the task? Or
Yeah, like software kind of like, you know, so in that way we can transform the problem into kind of like a GNN setting. So it's like we use like a graph to train and then do the detection. So I don't know if that's kind of like an interesting question.
I think that's quite interesting, and I will see that maybe we can have some possibility to explore that. Especially when we have some data or some graph in the past, we can do it to train and to predict what the market will be like in the next step. I think quite interesting.
Because I think like you talk about temporal as one by that's also like quite into
Yeah.
general thing. And the third question, so the last one, so I think like what we are really like the algorithm doing is kind of like a web representation review. Exploration, kind of like we are kind of running like a motif of like the.
Actually, you can consider it as a motive, but we are not using any learning method to do the representation. We're just using the graph mining method to it's actually quite similar to subgraph mining to find the cycle pattern in the graph and trying to detect the most negative one. Thank you for the question.